Hey there, welcome back. So here's a game I was working on a few years ago. Now it's not complete, so I just abandoned it. But I want to show you something. Here I'm walking from screen to screen, so nothing special so far. So I get over here, a few rooms over. And now, if I go into that door, continue on, and when I walk into this door, something else happens. Now I'm in this shop, which changes the gameplay totally. Here, instead of controlling the player, I'm controlling this arrow on the top. Back and forth, left and right. So I'm not controlling the player anymore. This is a completely different screen. And let's exit this shop now. Now I'm back in control of the player. How am I doing this? Let's take a closer look. So, before we begin today, I just want to mention something in case you didn't see it on my community post. Yesterday I did some updates on the book, so now there are slight updates on the book, which means that I've fixed 3 minor mistakes, which we're gonna come back to in just a second. And also on the book, the cover is correctly aligned. And also for those of you who have been waiting for a paperback version, there's also a paperback version available now on the Bookstore. So let's take a quick look at these minor mistakes. So the first one is at page 68. So let's just go to page 68 here. Let's see. There we go. So here I have said that FFFF is 65,536. This last digit should be a 5, not a 6. So 65,535 is what it should be. So that's the first mistake. The second mistake is at page 130. So let's see, 130, that's here. Yeah, here it is. So here I have written load A with this binary number. Now I forgot to put a hash sign in front of this percent sign. So there should be a hash sign in front of this percent sign. LDA space and then a hash percent, because this is you're supposed to load a number, this as a number. So there's missing a hash symbol in front of this percent sign at page 130. And then finally, the last mistake is at page 244. So let's go there. 200 and let's see, 44. Yeah. So here when I'm using let's see. No, sorry, not on this page. It's here when I'm using OR. Sorry, page 247. So here I'm using OR with the zeros and ones, and it says 1 and 0 is 1. That's correct. 0 and 0 is 0. That's correct. But here it says 1 and 0 is 0. There should be a 1 here. Right here. There should be a 1 there. So because 1 and 0 is 1. So there should be a 1 here instead of a 0. Those are the 3 minor mistakes that I've now fixed in the book in this new version that I have uploaded. So, over to today's episode. So, what I showed you in the intro, like I said, was just a game that I worked on a few years ago. But the point I wanted to make there was that just suddenly flipping a screen to a different screen is something that can be very useful when you're making a game. Like we saw in the example. The guy was walking around and then suddenly we have this store screen. And suddenly we go back to the normal screen again. Now, of course, you could have loaded in the graphics for the store and then loaded back the graphics for the level. But if you do that, you can't pause the game. Let's say your player is jumping and you want to switch over to a menu. And when you go back to from the menu to the game, the player is still in the air because you were jumping. So you want to pause the game before you switch the menu. Now, if you just switch screens, that makes this much easier. So, of course, what we're talking about here is screen RAM, changing where screen RAM is. So, let's just start with a very quick repetition. Now, of course, you probably know this already. We have this DIMM RAM, the Commodore 64. We have 64 kilobytes of memory, over 65,000 memory addresses. But let's look closer at this part here, because this is where screen RAM is by default on the Commodore 64. So it's at memory address 0400. That's where screen RAM starts. But the thing is, now we have talked a little bit about this before, but the thing is that we can change where screen RAM is on the Commodore 64. Now, of course, the natural question would be, why would you do that? But I've already answered that in the example I mentioned. Like in a game, if you, for example, want to quickly switch over to a menu or whatever other kind of screen you want to switch to, you can do that. And you can prepare a screen. We saw this in the scrolling tutorial when we're preparing a screen in another part of memory. Now, screen RAM isn't pointing at that part of the memory yet, but the graphics are ready over there. So if we quickly want to switch to a different screen, then we can do that very quickly and the graphics are already there. Now, like we saw in the scrolling tutorial, unfortunately, the colors aren't there. So we have to do some work getting the right colors there. But at least we're saving a lot of time we don't have to draw the graphics. You can switch back and forth between two screens. So we're starting at 0400. Also, we need to be aware of something, because the VIC chip can only see a part of the memory at any given time. So it can only see 16 kilobytes, which means it can only see this part of memory, or let's see, 1, 2, 3, 4. So you can see this part, or this part, this part, or this part. So you can only see the memory in chunks of 16 kilobytes. So if by default it's set to this part of the memory, the VIC chip can see this part of the memory, which also means that we can't put graphics like sprite data over here if by default. So we can put sprite graphics at memory address 2000, for example. That's no problem. But we can't put them over here if screen RAM is set to this part of the memory, or sorry, the VIC chip is set to this part of the memory. Now, I don't want to make this too complex right now, but it's just something to be aware of. So let's just look at this part, the default part of the VIC chip, the first 16 kilobytes of memory. So right now, like I said, default we're starting at 0400. That's the screen RAM is by default. So I made a very small example here where I'm just reading the keyboard, and if I press 0, then the screen RAM goes to 0400, which is default. But if I press 1 on the keyboard, then screen RAM is at 0C100. So I can switch back and forth like that. So let's just take a quick look, see what that looks like. So here we're starting up, and of course now screen RAM is at 0400. So if I press 0 right now, nothing's going to happen because we're already at 0400. But if I press 1 on the keyboard now, then the screen RAM will switch over to 0C100, which is what I set up here. So now I'm going to press 1 on the keyboard, and now the screen looks like this. If I press 0, then I go back to 0400 again. So right now I can switch between two different areas in the Commodore 64 memory. So I'm changing where screen RAM is. But why does it look like this when we're at 0C100? Well, I think we mentioned this back when we were talking about scrolling. But let's just repeat this. If I open up a monitor now to look inside the Commodore 64 memory right now, so I can go to File, Activate Monitor. Okay, there we go. So now I can take a look inside the Commodore 64 memory as it is right now. So I'll just write M for memory display, starting at memory address 0400. So now we're gonna see what's inside memory starting at 0400. And that's this. Of course, it's just numbers. We know that. There are only numbers inside the memory. But if you look over here, we can actually see, remember, these are screen codes, right? Because this is screen RAM. And all of these are hexadecimal numbers. So all of these 20s, hexadecimal 20s here, those are space characters, because there are a lot of space characters here on the screen. So all of these 20s are these space characters. But if you can look over here, we can actually see what's inside. Commodore 64 Basic V2, 64K RAM system. Yeah, exactly. That's what we have going on here. So that's what's inside the screen RAM area right now. But what if I change over to 0C100 so that screen RAM is at 0C100 like this? What's inside memory right now? Okay, let's take a look. Go back to the monitor, and now I'm going to write M0C100, and look at that. Basically we just have 00 and FF, 00FF. Now FF, of course, that's 255. So that's basically what we have here. The memory is filled with zeros and 255s like this. So that's why the screen looks like this when I switch over to 0C100. So when screen RAM is at 0C100 right now, it looks like this. And you can see that over here as well. So basically what we can learn from this is that the VIC chip on the Commodore 64 is not smart. It doesn't do any super cool things like checking this or that. It just displays whatever screen codes is in screen RAM. So like we saw here, if there are just zeros and 255s, then this is what we'll get. Now if there are more structured screen codes like this, then it makes more sense. So it's just something to be aware of, that when you're making games, making background routines, whatever, we have to be absolutely sure that we know how screen RAM works. Alright, so let's take a quick look at what I'm doing here in the code, because we're talking about memory address D1018. D1018, that's where we are changing where screen RAM is, but that's also where we're setting where the character set is. So by default, the value inside there is 0001. The 4 bits on the left there, they say where the screen RAM is, where screen RAM should start. By default, that's a 0400. The next 3 bits says where the character set starts. By default, that's at memory address 1000. So we need to mix the first 4, or the 4 leftmost bits. Those are the screen RAM. So we need to set some kind of combination there to decide where screen RAM is, and the next 3 bits is where character set is. So how can we find the bits we need to use? Well, we have this great site here by Joe Forster. He has basically documented almost every memory address here on the Commodore 64. So we have seen this before. But here he talks about memory address D1018. Now we need to use sort of a list like this to keep track of this. So like we saw, the 4 bits on the left in D1018 are where screen RAM starts. So we can choose between these addresses: 0000, 0400, which is the default one, 0800, 0C100, and so on. So the way we do that is we set these bits right here in D1018. So the 4 leftmost bits are what decides where screen RAM starts. The next 3 bits is the character set. So, like I said, we've seen these kinds of things before, so we don't need to go too deep into this. But we do need to know how D1018 works. So, these numbers, or these bits, did they just throw some random zeros and ones here and say, well, this can be 400 or whatever? Well, no, it's actually a system. So let's take, just use this calculator. If we say 0400, the default one, and if we only look at the high byte here, 04, because they all end with 0000. All of these starting addresses for screen RAM end with 00. So let's look at the high byte. And let's start with high byte 4 here. So if I say 4, hexadecimal 4, I don't know if you can see it, but here we have the bits that represents this number, and this is the 4 is right there. So what happens if I bit shift twice to the left now? Once, twice. If we look at the bits here, it's at 0001. If we look at this on the website here, it's at 0001 for 400. So basically what we can do, we can bit shift twice to the left. We can use this number, the high byte number, bit shift twice to the left, and then we get the right bit combination here for screen RAM. So I did that here. I made a little another example. So this example reads 8 keys on the keyboard from 0 to 7. And here on the bottom I made a table using the high bytes where screen RAM starts. I have 00, 04, 08, 0C. So these are the high byte for the starting addresses of screen RAM. I didn't include everyone here, but just the first 8 ones. So let me just run this to show you. So of course we're starting here at 0400, and if I press 0 now, this happens. Now screen RAM is at 0000. Now there's a problem here. We're going to come back to that in just a second. If I press 1, then screen RAM is at 0400. Now that's the default one, and this looks wonderful, no problem. We're at 0400 now. Screen RAM is at 0400. If I press 2 on the keyboard, then screen RAM is going to be at 0800. Let's see what that looks like. This is 0800. Now screen RAM is at 0800. So not too bad. Little random characters here, but you know, not too bad. If I press 0, 1, 2, if I press 3 now, then screen RAM will be at 0C100. Still, it looks okay. If I press 4 now, then screen RAM will be at memory address 1000. What does that look like? Well, there's a lot of weird stuff here. I don't know if you noticed it, but I'm writing hello here up in the corner. And for 0400 it looks okay. 0800 looks okay. 0C100 it looks okay. But here at 0000, we're at the very beginning, we have problems. Here at 1000, there's also a little issue. It doesn't say hello up here anymore. So there's a lot to think about here. First of all, if we put screen RAM here at the very beginning at memory address 0000, think about this. What's at memory address, starting at memory address 0000 at the very beginning? Well, if you have been following my videos, you know that that's the 0 page is. The first 255 memory addresses of the memory is what we call 0 page. Those are very special memory addresses. Yeah, we use them for a lot of things. So that's the first 256. Now from memory address 0100 and onward, that memory area is the stack. So 256 bytes for the stack. And we have a lot from memory address 0200. We have a lot of special things there. So here in this Excel spreadsheet, I just wrote that this first part of the Commodore 64 memory is the Commodore 64 system, because there's a lot of special stuff there. So we shouldn't be using that unless we know what we're doing. And in fact, if we put screen RAM there, let's see, we get this. We have 0 page here, we have stack, we have it's just not a good place to put to use as screen RAM, because there's a lot of other stuff going on in that part of the memory. But at memory address 0400, it's of course no problem. But what about memory address 1000? Why doesn't that look okay? 0400 looks okay, 0400, 0800, 0C100, all those are okay. But once we get to 1000, so we have 0400, 0800, 0C100, all those are okay. We can see that it says hello up here. But when we set screen RAM to 1000, we just have a lot of random stuff in here. So that's because at memory address 1000 we have the default character set. So again, there's a lot to think about, but what we should learn from this is that we need to be careful where we place screen RAM. We can't just use whatever memory address, especially here in the beginning. So we should stay away from the addresses before 0400, and using memory address 1000 is also not a good idea, because that's where the character set is. Now, before we look more at the code, let me just mention one more thing. We've talked about where we can't or where we shouldn't use screen RAM. So we've seen that using screen RAM at the beginning, where we have 0 page and a stack, is not a good idea. 0400 works okay. Also, we need to mention that here at 0800, which I have right now, should probably be a little bit careful, because you see there's some random characters here at the beginning. So at 0800, remember that our program starts at 0801. That's where the default start area. So from there on out, we have the basic loader. So 0800 might not be the best either. So there are many places in memory where you have to be careful. Okay, but let me just show you a little bit more about how I set up this code. Now, like I told you, I'm just reading the keyboard and I'm checking for characters or keys 0 to 7. So what happens if I press one of those? Well, I just jump down here to where it says set screen RAM high byte, because I just need to set the high byte, since the low byte is always 00. So when I press a key, the key is translated into a PETSCII code. A PETSCII code, if you remember, it's almost like screen code, just a little bit different. And hexadecimal 30 here, that's the PETSCII code for 0. So when I press 0 on the keyboard, I will get hexadecimal 30 here into the accumulator. And I'm using the kernel functions scan key and get in here. And after running get in, I get whatever pressed on the keyboard, I will get that PETSCII code into the accumulator. So that's why I don't have to write LDA first here. I just write compare 30, because the get in routine already put something in the accumulator. Alright, so I'll get 30 or 31, 32 based on what key I pressed on the keyboard. So then after I've pressed a key, I jump down to here. Remember, I already have a number in the accumulator. But then I say AND with this. So since I already have something in the accumulator, I can use AND now. And let's say I pressed key 7. That would send hexadecimal number 37 into this. So now I would have 37 in the accumulator. And I made this table down here, 0, 1, 2, 3, 4, 5, 6, 7. So I have entries, 8 entries here from 0 to 7. So what I do here, since I'm pressing keys from 0 to 7, which is 30, 31, 32, 33, and so on, I just want this last digit. I don't want this 3 here. So I'll just write AND 0, 0, 0, 0 to blank out that part of the number, or that nibble. We talked a little bit about this before, but basically I write LDA, or in this case, this routine has put something into the accumulator for me. So when I get down here and say AND zeros over here, I blank out that nibble in the byte. So I'll just end up with 6, 7, or 5, whatever the other nibble of that byte was. So why am I doing that? Well, here I say, then after doing that, which means if I pressed 5, which would give me 35, but I blanked out the 3, so now I just have 5. Transfer A to X. Now I would transfer 5 to X in that example, and then say LDA screen RAM high byte. So this table, comma X. Right, so this table is down here. Let's say it was 5. 0, 1, 2, 3, 4, 5. Then I would get this. And then I say here, so now I will get that number and store it in a memory address 0288. 0288, that's a memory address on the Commodore 64 that keeps track of, or where you should put the high byte of screen RAM. It's not necessary in every case, but in cases like this, where I'm using the kernel routine to write characters, then I need to do this to make it work. So I put the high byte, which I got from my table down here, I put that into memory address 0288. So now I've done that, but after that I do what we saw here in the beginning. Let's say 14 here, hexadecimal 14, that's the number I got. Okay, so after storing the high byte number into 288, I bit shift twice to the left. So let's do that with this number. Once, twice. So again, I don't know if you can see it, but this binary number is now, after bit shifting twice to the left, 0101. I store that in this variable called temp. Then I say load whatever's in D1018 right now, blank out those leftmost bits because I want to change them now, so I need them to be 0. But then I say OR with whatever I put in temp here. What I put in temp was these bits here, 0101, or this entire number, but the last digits are zeros. The point is that right now, by ORing, first clearing those bits and then ORing it with whatever I put in here, storing it back into D1018, that will set the correct bits. So here in this case it was 1400 to use that as the starting address for screen RAM. So the point I'm trying to make here is that you can make systems to change screen RAM back and forth. But as you can see, things quickly get a little complex. So like I said before, you absolutely need to know the basics. And I'm not just talking about LDA, STA. You also need to know about working with bits, ANDing things, ORing things, and also bit shifting. So all of these things are things you need to be comfortable with. But once you're comfortable with that, then you can start making systems like this, where you set up a system where it's easy to switch where screen RAM is. And once that's in place, then you can include that in the super cool game that you're going to make with menus or shops or whatever. So, sorry if this was a super technical episode or not too exciting, but remember, I'm not making videos to impress people or to make super exciting stuff. I'm trying to help people get started programming in assembly language. So anyway, I hope you got something out of this. I hope you found this useful. That's it for now. So I'll see you in the next video. Bye bye.